example, in those traditional robots, the function and the structures, they are separated. But if we look at ourselves, we have all the structure units, actuation units, sensing units, or many other units. They are highly integrated. And actually, smart material can be a bridge which can help us to fusion those units and to integrate that the material structure and the structure and function and the actuation and sensing and all the other functionalities. So this is I think the rule of the smart materials. And what are the smart materials? I think everyone are very familiar. Smart material, it's the material which can sense the environmental stimuli and then response. And the response could be the property change. The environmental stimuli could be something like this here, right? And the property change, can be like the change in shape, or like the if we say that it's a general property change, it can be like the change in property or change even like in functionalities, right? And there are a lot of smart materials such as shape memory polymers, liquid crystal elastomers, and a lot. But if we want to develop like the next new generation of the smart structures, we have like new requirements, such as the structure should be in lightweight, like the small size, or have a lot of functions that are highly integrated. However, the current manufacturing methods, such as the casting or cutting, cannot reach these goals. And then the additive manufacturing or 3D printing is a very advanced manufacturing tool. And if we use 3D printing to print that smart material, we can realize these goals. And that's the reason we start with like 4D printing, with 3D printing smart material, and then we print that structure that can change its shape over the fourth dimension. And here are like two typical and pioneering examples, which was like presented 10 years ago. 10 years ago. But the last 10 years, there are great advances in 4D printing. And the example of the 4D printing are not limited in like the shape change. Here, like the structure can change shape, but also can like the stiffness change. We can also use the property of the stiffness change of the shape memory polymer to do some like the stiffness variable soft robot. Or can be like a color change. We can develop some material which the color is can be changed if we change the temperature. Or we can even use the two-photolithography to print some like the structure colors. And then if the material is shape memory polymer, we can also realize that the structure color change. Or even we can print some like the conductive material, and then we use such conductive material to print some sensor, and then we can realize that the signal change. And the 3D printing technologies, we can use to print smart material, especially for the soft smart material, can be like the PolyJet printer, or like the DIW, direct ink writing, or DLP, digital light processing. And compared to others, DLP is a very unique one, because we can print the 3D structures by like slice into the different layers, and then use the DMD to project the the UV light onto the polymer resin surface, and then to localize the polymerization, and then to print the patterns layer by layer, and then we can create some structures with high resolution and even like multi-scales. Compared to other 3D printing technologies, DLP can realize that fast 3D printing with high resolution, or we can also print a very complex, highly complex 3D structure, high resolution and the large area, and also it is available with a wide range of printable materials. And as I presented, in a few slides earlier, we can use like the DLP to print some very high resolution structures and some like lattice structure can be like used for aerospace applications. But could we use the DLP to realize that multi-material 3D printing? So this is a good question. But because DLP, we do the printing in the liquid environment. If we want to do the multi-material 3D printing, actually we need to change or to switch that the printing environment. No matter the light is top down, or the light is bottom up, we always need to change that the printing environment. But if we change the printing environment, or the contamination always exists. For example, like we print that structure into the liquid, the resin, and then we finish the printing. We take the printed part out of the liquid resin. Always have that residual resin, stick onto the printed part, and then if we directly immerse, this printed part into the yellow resin, then the contamination occur. Here is an example we show. If we do not take any other action, contamination happens. Even print one layer, see that the result is very poor. And there are a lot of approaches. People try to remove the residual resin, such as combine like washing or drying or like wiping or like air jetting. There are a lot of papers, about that to use this method to realize high quality multi-material DLP 3D printing. But for this approach, there are always the direct contact of the solid vapor or fluidic flow onto the printed part. Then we have the limitation, like the structure cannot be very large. And the material are very, limited. For example, like a viscous material, like the ceramics, we cannot print. Or the integrated function integration are very limited. You can only like have a few functions. And how could we, to address these challenges? We inspired by nature. You see that here is a dog. The dog shake its the body and to dry itself. And actually, the dog is smartly use the centrifugal force to remove the liquid. And actually, we find that the professor David Hu from Georgia Tech School of Mechanical Engineering, he did some very interesting work 10 years ago, and just started that how that the dog or the mammals to shake its body to attempt to remove to dry itself. And compared to other methods, this method allows the dog to dry itself with a very fast speed, just a few seconds, and it's independent of the body size. It doesn't matter it's a big dog or a small dog, you can always dry it very quickly, and no contact. A dog does not need a towel. Right? So inspired by the dog, and then we develop a 3D multi-material DLP 3D printer. We call the centrifugal multi-material 3D printer. The only difference, between the previous 3D printer is that we add 1 degree of freedom on the printing stage, and we let the printing stage quickly spin, and then use the spin to generate the centrifugal force, and then we can quickly remove that residual residual resin, and then we can print very large, two material structure. And also, if we add multiple, the resin container, we can print a lot of different materials in one layer. And here is the video showing that the printing process. So we print black material, then we use the spin to remove the material, and then we print that white layer. And after 100 layers, then the resin, the black and the white resin container are still, the material are not very badly contaminated. And also we did a lot of study to start to understand, how that the spin speed and the time on the residual resin removal. For example, like we find that of course the longer time or like a single residual leads to the thinner residual layer, or like the faster, the spin speed, we can get a thinner residual layer, a lower viscosity, and then we need less time to remove the residual resin. And of course, that the efficiency of the residual resin removal is independent of the size of the residual resin, and then after spin, that the thickness of that the thin layer is almost uniform. And in order to, because we will print different materials with different viscosity, in order to guide us to find the right, spin time and the spin speed, and for different, the residual, the resin viscosity, we develop a model, use that fluidic mechanics, and then we build the relation that if we, for example, we need to reduce that the layer of the residual resin into the 10 microns, how to change that for example, the spin time, or the spin speed, and then we build that design map, which tell us different viscosity and the different spin time, and then for the different material. And also using this, our 3D printer, we can print like a wide range of materials, from hydrogel to ceramics, and then the modulus can be changed, from a few kilopascal to like even like a few hundred megapascal, and the viscosity also covers a lot, for the very low viscosity hydrogel to very viscous ceramics. And here shows a few examples. We can print that hard material and the soft material together. We can print like the shape memory polymer. We can print that the rigid panel and then the shape memory polymer hinge, and then we can build the origami structure and with a shape memory effect. Also, we can print some flexible electronics, and we can print that the core part is ionic conductive, and then the outside part is non-conductive. We can even print polymer and ceramic together. And of course, this is ceramic green body, and then after printing, the green body, we need to do the sintering and to remove that polymer part. How to use that? Actually, then we can use that polymer part as a support material. Here we show example like the ceramic bearing. Ceramic bearing have the ring, and then the ruler, and the ruler actually is no contact with that the rings, and then in the printing process, actually it's impossible. But if we do that two material printing, in the printing process, we have that polymer as a support, and then after printing, we do the sintering, and the sintering can remove that the polymer part, and then we have that the rulers which can freely rotate. And then this ceramic bearing, can use to connect that here is here is that it can rotate freely, and of course because the ceramic is less heat conductive, and then we can see that actually the heat is not quickly transferred to that shaft. And we also compare our the 3D printer's performance with other already developed 3D printer, multi-material 3D printers. The key actually for multi-material printing is that the transition zoom, between the dark and the black and the white material. For ours, the transition for the current system, the transition zone is about 100 micron. But for the like the polyjet, here is like a 400, and here is like 250. This is the Gentry Lewis material, the multi-material 3D printer. And also we can print some like the digital material. Like we can control that soft vessel and hard vessel, and then we can, by controlling that the version, between the ratio between the soft and hard voxel, we can like use two material to tune that the stiffness of the material of the printed part. Here shows one example. Like this is a pure soft material, this is pure hard material, and then you see that if we have a layer of hydrogel, and then you see that the band, because the stiffness is different, the bending is different. And also we can use this approach to develop that a soft robot which with multi-sensing capability. We can print a lot of different sensors, like a bending sensor, like the temperature sensor, or like the pressure sensor in one printing process onto that soft robotic finger, and then this finger can sense signals like bending signals, and the compression sensor will have different response if it grabs different objects. And also because we have that temperature sensor, and then we once this the robotic finger to grab different objects with different temperatures, we found that actually the pressure sensor will be the data is not right, because the data also varies with temperature. But now we have the temperature sensor here. We can use the signal of the temperature sensor help us to correct the signal on that the capacitive pressure sensor. And we also develop a lot of different UV curable and ionic conductive elastomer, and then use this material with that our multi-material 3D printer. We print that like the string sensors, which we can print a smart glove, which we can use to control a robotic finger, or we can print the pattern onto the substrate with different stiffness, and then we can use that to create some force sensor. And also we can print that use multi-material 3D printing to print some high performance capacitive pressure sensor. And if we design that the dielectric layer of that the capacitive sensor, then we can improve that the sensitivity of the sensor. And also we can quickly print an array of that compressive sensor, and then it can to sense like the touch in different direct location. And also we can to print a sensor, a capacitive sensor with a multimode sensing capability, as like our skin. Our skin can sense different pressure, like a compression, tension, or even like compression plus shear, or some other ways. And using our multi-material 3D printing capability, we can print like the capacitive sensor, not only like this typical sandwich structure, which can be used to sense tension or compression, but also we can use like the design like this way, and which can be used to share that to sense that shear signal, or design the sensor like this way, which we can use to sense a torsion. And also we can develop using some smart design. We can develop some sensor which we can use one sensor to sense both compression and tension, but the two signals, they don't interfere with each other. And also we can develop a sensor which can sense compression or shear, also don't interfere each other, or torsion and compression. Okay, and last but not least, I want to spend one slide to talk about the perspective of multi-material, multifunctional 4D printing. So now we use the 4D printing. We can print. We can print a smart material to create smart structures. But our ultimate goal is to, to print some smart device, smart machines, or even smart systems. But how could we, realize like the smart systems? I think still there are, some challenges in the three aspects. One is that manufacturing, current 3D printing capability is still not, enough. We need to develop more like a multi-material 3D printing capabilities. And also we want to, to have that multi-scale 3D printing capability. We want to print a structure with a very refined, feature, but the size is quite huge. And sometimes, one 3D printing technology can only, suitable for a few materials. For example, like a DLP, which can actually difficult to print like the metal. And therefore, we maybe also need to develop some like printing system, which is a hybrid, can combine different, printing, 3D printing technologies. And also sometimes we want to print like the sensors or some actuators on like the curved surface, and then we want to have that conform 3D printing technology. And there are a lot of other, possibilities. For the materials, I think of course, the like chip memory polymers or hydros, they are very good, responsive material. But, if we want to use them for like the robot, I think, they still have some limitations. Therefore, if we can develop some real like a muscle-like material, which can be 3D printable, I think that would be beneficial, for realize like the 3D printed robot. And also, if we want to have a robot, we also want to have like the energy storage part. We want to have some like the part which can like transfer signals. And therefore, we need to also print some like flexible material with high conductivity. And because, the system have different material, then those material, they are dissimilar. And then the bonding mechanism, for those dissimilar material are also very important. And the last is that design. Design is also very important, for the multi-material and the multifunctional 4D printing, especially for this time, the problem becomes the inverse problem, design problem. And also, the for the 3D printed part, it is like the Voxel-based material distribution, other than like continuous material distribution. And so the design problem would be challenging. And also, the design, if we use that, the topological optimization, it's usually for the pure mechanics problem. And now the problem becomes the multi-physics. And also the objective is changing from the just optimize or the reach a target goal for the mechanical property to like the capability of motion sensing or like the mass or heat transport. And this is the perspective of the future 4D printing. And then last, I want to thank my research team, especially like my PhD student, Jianxiang Chen, who built that multi-material 3D printer, and Xiangnan He, who built a lot of like the ionic conducting material. And also, I like to thank my PhD advisor, Professor Jerry Qi, and Professor Martin Dang, who brought me to this fantastic world of 4D printing. And thank you all for your attention. That's my presentation.